I'm Alejandro Martinez. I work at systems at Cars2DV. And well, there have been a lot of talks already about Cars2DV, which is, I think, the easiest way to get your data in a maps in a couple clicks, by just uploading the data, be a CSV, a shape file, or an Excel file, and just in a couple clicks style it and get lots of analysis and insights for it and sharing its visualizations. But I'm going to talk more about the insights on the headaches we've gotten to get this thing to work properly. Because we've run pretty fast, and we've run from being a small system based on completely open source stack, and actually the whole Cars2DV, or almost all parts of it, are open source. And we're using lots of awesome apps from the open source community of Postgres, Postgres, Mapnik, Gitl. And there are building blocks, and we're building on top of them, and also making an open source platform which we're using to serve millions of tiles every day to all parts on the world. This is actually a heat map of not from where people are that are looking at tiles, but the tiles that we're actually of the tiles we're actually serving all around the world. This is a day that had a bit of activity due to some news in Spain. And we're serving a lot of dynamic data. But the magic thing about us, because we're open source, and anyone could replicate us pretty easily. But the magic part we have is the maintained cloud environment. You just give us our data, style it, and customize your SQL and the way you want to visualize your data, and we'll serve it for you, and we'll be sure everything keeps working right. And in this regard, Cars2DV is different to other solutions, I think, because we're dynamic in the sense we're too dynamic, as we allow users to do anything they want with the data, using the SQL API to update the data and make it automatically refreshed and rendered again on tiles. In this case, it's an example of an application made by Fulcrum, which is using a mobile app for gas inspectors to log where they've done inspections of gas infrastructure. And it's serving hundreds of gas inspectors on a map that is refreshed in real time, so you can see which inspections were done yesterday, today, filtered by using SQL, in this case using Cars2DV AES to filter which section of data you're interested in and change the style. And of course, we're highly dynamic, but sort of dynamic, because all the information you see can be updated in real time and will be refreshed in real time. But we also have to be aware of an important component of this dynamic part, which is that most of the dynamic maps are static in their data nature. Even this animated map, or tweets during the Super Bowl, which is one of the huge numbers of Twitter maps. This will be the last Twitter map I will be showing today. Actually, it is static in the sense that the data doesn't change, and it is served to millions of people, but the data behind it never gets refreshed. It can be refreshed if the author of the map decides to put add a day more of tweets. It will be rendered, but we actually most of the maps and things we're serving being sort of static, because if not, we'll be rendering the same thing once and once and once again, and we'll be just wasting CPU resources on rendering and change things. And well, that's why we need a cache layer, and it's a very complicated cache layer, because the way we have it, any moment anyone updates the data, we have two layers of caching. One of those is some internal HTTP caching we run on top of Varnish, and then on a CDN caching using Fastly, actually, on hundreds of points of presence around the world that we have closely monitored. For example, this is a day worth of a request from one server, and actually of this match, which is all of the data we're serving, we're actually just rendering a couple of these. And even that, a lot of the data in blue, which is the cache misses, come from our internal caches. So we rely on that a lot to actually being able to scale maps to millions of viewers, because actually the read to write ratio on a platform is very high. Even though if you want to write, we'll share you can write. But right now we're focused on being able to read hundreds and hundreds of times, and actually being able to invalidate with multiple contraptions. For example, this one is a bit of SQL trigger invalidating on Varnish, done in Python inside SQL, being loaded by a Ruby code. I just wanted to put it because it's I love the contraption we've gotten around to. But yeah, the fact is we're actually very flexible, but we also have very control on what users can do. But we're flexible in the sense that any user can upload any geometries and data they have, and then run any SQL query that gets out of their heads to do operations with it, and then render it using the rendering layer, which is our entire code called Winshaft. I'll get to that later. With any SQL and CSS they desire. We're giving power to the users to do big things, so they can upload their own huge geometries, like hundreds of megabytes of polygons, and they run any kind of geospatial operations on top of them, and they can render it with any SQL and CSS they want. Even though that, from a system side, that looks and is a bit of a hell, actually, because most of the geometries that users upload that are not that optimized, and they got, for example, a huge precision. For a use case, they don't want to see, for example, they're uploading data with meters or centimeters precision of a country for just showing the overview of the country and wasting space in their accounts and resources on that. And also running geospatial operations that are pretty heavy because PostGIS has some very good things, but also some not really optimized things. And then rendering it by using some SQL that most of the times is not the ideal thing for the job. But we have no automatic way to tell that to the users, so we have to live with it. We live with it, but we try to pinpoint it at trying to learn how users are doing their stuff, at keeping close metrics on every server, database server, and every user. In this case, this is our internal dashboard we have. This is not for the whole category platform, but for a subset of users. We're keeping track of the variances in response time, on target requests, on SQL API responses. But the thing is that as we allow users to do anything they want, we can bound and be predictable and say all of the queries will take less than 100 milliseconds because sometimes it takes a lot more than that to just get the SQL results of the geometry they want to render. So we're actually closing the walls of this flexibility because the problem is that it ends up hoarding because users share a database server and a Postgres instance, and Postgres has no built-in way to restrict the CPU usage or the queries a user wants to run apart from setting a timeout, so queries don't take longer than, for example, 5 minutes. So we're actually working on that too, with another layer on top of Postgres, which will allow not only limiting by statement timeout, but also using Linux C groups to actually give the processes of each database connection a different priority on the database. So we give them power, but we'll limit the CPU power they use so they don't hurt other customers. And to get a bit of a history of how we grow up the platform, I want to explain that at first, when we were very small and we were in the hundreds of users, all of the category was just the bare metal servers, which all of the parts of the rendering things in one single machine. The database, the SQL API, which is an API you can use just to throw SQL queries to the database server. Our target service, which is open source too, which is Winshaft CartoDB, which is built on top of Mapnik. And then our management UI, which is the interface you see, which is made on Ruby on Rails with a hefty lot of JavaScript client-side code. And what we did is just this. We just, as we need to scale and put more users, we just started sharding the users. This is not the real distribution, but sort of adding new servers to the thing and distributing users between servers. But that sharding problem gets to be it gets to be not so convenient when you have a single user which is hammering the server a lot and getting to the whole potential of the CPU of that server, and then we have a lot of idling resources on all of the bare metal servers all around. So then there was a point where we said we have to scale, and we moved to Amazon EC2. And inside we moved what was previously inside a single machine. We just distributed it over machines, so we can now share parts of computing power among the tiler, the SQL API, and the Rails side, and actually reuse them for different database servers. The only thing that is unique in CartoDB to an user is the database server, which means each user is only on a cluster, be it replicated or not. And then the rest of the things are shared. The tilers actually render tiles from all the machines. The SQL API connects to all the machines. We have some sort of prioritizing. So enterprise and paying users get more resources, get to do more queries and get their traffic prioritized against the free users. But that is the way we're going for now. And sorry. Once you remove CPU from the equation, it is no longer your bottleneck. But when you start moving out things and using things the way they're not supposed to be, you find out a different kind of problems, which is the bottlenecks that aren't there until you find them. For example, there was a client which just served data from a relatively small database. Which were those tiles. In this one, for example, this one is just empty. Well, it is actually the middle of a polygon, and this one is actually also, I think, a polygon. The data, I think, the source was a rasterized polygon for some reason, and we noticed that when we moved from the dedicated instances and putting everything in the same machine to putting everything in distributed things, everything started going. This client in particular started going more and more slowly. And we couldn't figure out why. So we started looking at the data set, and we figured out that the polygon that those two tiles are rendered for is actually 25 megabytes of data, which is stored in the database. And that PostGIS and Mapnik, the polygon and the intersection cutting of PostGIS doesn't seem to be very efficient. So what Mapnik does is actually download the whole polygon and then paint it. The problem is that when the tiles, you get in that part of information from a big polygon, but also it sounded like too much. So we started to look at the protocol that PostGIS uses to communicate with Mapnik, and it was just and also the internal protocol it uses, which is the WKV. And we found out that all of the data between the poster server and the tiler server is sent in WKV, which actually has an 8-byte float for each X coordinate. That 8-byte, we're basically transferring all of the points of the polygon, 8 bits per byte, 8 bits per latitude or longitude, depending on the pattern of the coordinate, over a single network link. So what happened? We just went to the monitoring tools, we looked at the traffic, and we found that the reason that everything was going wrong was because we were actually collapsing the network interfaces of the machine, transferring data, which we did the math, and the data turned out that for each tile that we're rendering, we're transferring 25 megabytes of data, which is all of the points of the polygon with a 8-byte precision, which is actually a precision of 2.17 per 10 to the power of minus 10 precision. And yeah, this was our face when we found that out. And because of the fact that this data was looked almost half the data, almost everything on the data we're transferring is looked at high tune levels or relatively high. So even a meter distance would be enough. But 10 to the minus 10 centimeters sounded like definitely too much. We started doing some tweaks with using a hacked up version of both PostGIS and Mapnik to actually use a format we call CDVWKV, which is a stupid format, which is just get the bytes and get the precision to a half. And that is like 100 centimeter, no, 1 centimeter precision, that for high zoom levels is even less than a pixel, and nobody will notice that. And we're experimenting to it, but instead of the solution, we're actually we want to do it the clean way, and while we work on the real solution, we just decide to scale the process part and then add some slaves so we get some traffic to kill with too many precision of data. Until we get to a solid solution, for example, the one we're thinking is to just inside the Postgres and the tiler WinShaft, we're thinking of adding something that packs the data and then caches it, because most of the times users are not changing SQL or the source of the data itself, but they're changing styles. And we don't need to get the whole data from that, and we want to get away with not hitting the database server as much as we can. And we're still working on that, and one of the approaches we're investigating is just to use mapnik vector tiles at the output of the Postgres, and then put a cache in the middle, so we can just use the same data for both rendering tiles using mapnik 2 on WinShaft on the server, and also sending the same mapnik vector tiles to client by using client rendering, which is something we're also working on. And this is just one of the bunch of problems we're having with scaling, and they're pretty fun. So if you're interested, we're looking for some people. We're growing. We just got some money, and if you're interested, we have a job page with positions we're looking, especially senior site reliability engineers and developers, and all kinds of jobs with cool problems to work with. So that's all. Thank you. And if you got any questions, now's the time. Yeah.
One thing I do for my caching is I cache all the data. I copy all the geometries and all the other data for each map into its own cache table, and then I send it to the tiles, so at least there's no subqueries. But I'm interested in your WinShaft and how is that faster than TileStash, or how that compares, and why you went with that, because I'm right now using TileStash to make my tiles. So.
Yeah, actually, there's one right there which might be more suitable to answer the question. But WinShaft was done, I think, before TileStash, so they're pretty compatible. WinShaft was developed in-house by CarDB, even though it's open source to more or less fit the requirements we have. But basically, they're just a front end to Mapnik and the way it does things behind. So yeah, in that regard, it's more or less comparable. But TileStash has a lot of good things, and WinShaft has too. And WinShaft is just filling our needs, and we're actually thinking on investigating how it works, because it might be actually better than ours. And about the caching, the problem with this is that we allow the users to change dynamically the SQL queries. So it's a bit difficult to actually cache the data output itself, because we don't know how. First, there's a bunch of data, and then second, we don't know how often will the user revisit it, because imagine he's just editing styles in the CarDB editor, and we get to an SQL query, he's trying things, and we cache it to HAL, and that will be quite inefficient. So we're working on doing some more like caching on demand, like more caching the data that the users actually request. So we're not inside the tile, inside a bounding box, not the whole data, because if not, we'll have to cache maybe even bounding boxes or places where there's no data at all.
One of your last diagrams showed PostgreSQL, something MVT, and a cache. Is that a caching layer for PostgreSQL?
Where?
That one there. I was wondering what exactly the MVT was, and if that indicates
yeah,
caching.
MVT is an intermediate format which is actually being created by Mapbox, which basically means mapnik vector tiles, which is just a way to get the information of a tile inside a per buffer in a very efficient way, and to get all the information related to a geometry. So this we haven't developed yet, but basically we wanted to generate those tiles, because with those tiles, they're unstyled, just the geometries. We can just cache the geometries, the raw geometries, and then paint it differently on the tile or even on the even client side. Anything else? Okay, so we're done. Thank you very much. Oh, this. There's another question? No.
Oh, well, yeah.
Yeah, sure.
The part there where it says the cache above the MVT there, is that referring to a standard, varnish style cache or mem cache, or
We're
what kind of
thinking of
caching are
going
you
the
using?
varnish style cache,
Okay.
but we're most like that.